Can you see my screen now?
Yes.
Perfect. Right. Okay, let's get started. Okay, so during the weekend, I uploaded some practice assignment onto the canvas. I hope you had chance to exercise those assignments. Basically, I give you two practice, right? So the first one is the resampling, like the bootstrap. So as you can see, I gave you a sample from drawn from a population, and if you plot the density for that sample, you do not see the very familiar bell-shaped, right, distribution, normal distribution. So that's a non-normal distribution. So if you got a sample like that, usually it's very challenging for you to construct a confidence interval, 95 confidence interval for the sample mean or population mean using the normality assumption. So in this situation, so we can do like the bootstrap. So we can do the resample or the sampling with the replacement. So I give you the code. You can just run through those R code when you have time, and make sure you understand the theorem behind. And as you can see, if you use so you got a normally distributed distribution sample. If you use the normality assumption to calculate the confidence interval, that confidence interval will be very wide. The reason why is that because the way you calculate the confidence interval based on the normality assumption only applies to the normally distributed data. So in many of the cases, for example, in your study, so it's very likely for you to get some sample which is not normally distributed. Then, if you want to construct a reasonable or if you want to construct a reasonable 95% confidence interval, so bootstrap will be a good strategy for you. So that's one practice. The other one is like this. So this is we're gonna continue talking about this. The second practice I gave you is the R code by which you can calculate the joint probability. So for example, if we are considering like three loci, right, A, B, and C, in a backcross design. So backcross design is a simple version. Suppose we want to calculate the joint probability of this progeny. So this progeny has a very specific genotype. At the A locus, the genotype is 1. And at B locus, the genotype, at B and C locus, loci, the genotypes are both 2. So so last time we mentioned, okay, so this is how we can use the matrix notation to facilitate our computation in R. And this is the easy one. So so I gave you the code, so exactly following this equation. So if you can compare that code with this, yeah, they are identical. And after you plug in some numbers, for example, in the practice code, I gave you the number of the R AB, right? I believe it's something like the 0.1, and I also give you some number for the RBC, which is 0.2. So if you plug in those numbers in your code, you're gonna get the final answer. So this is the probability or the fraction that you're gonna see the progeny of this genotype among your backcross progeny. Okay. All right. So in the final, so when you have time, please, review some materials which is relevant to the matrix presentation like this. So how the matrix computation is performed. So something like this. And all right. So now we want to extend our knowledge to some like more complicated situation. So in this case, so we're gonna dealing with like F2 population. So actually, F2 design is kind of like an extension of backcross. So this is the backcross, the transition matrix, right? So F2 is actually like the squared of the transition matrix for F2 is actually the squared of the transition matrix for the backcross design, just like this. So then it's very straightforward. It's easy to understand why in a F2 design we will have a 4x4 table, right? This matrix, transition matrix. So when we consider like a transition from the first loci A to the second, first locus A to the second locus B. So this is the transition matrix, which is a 4x4. And I hope everyone can understand these formulas in each element, of this transition matrix. So this actually represents the probability, transition probability from genotype, the first genotype at the first locus A, right? To the first genotype, to the second locus B, and so on. So this is how we understand this. So in the final exam, so I could ask you to construct this this matrix for me, transition matrix, and I will give you some numbers for this RAB or RBC. And once you successfully define your transition matrix, TAB and TBC, and I will ask you to do some calculations. So yeah, so in the final exam, I'm going to ask you to use your R program to write some code. So you just follow the example I gave you in the practice. The only thing is like you have to expand that from the backcross design to the F2 design. So instead of using the 2x2 table, right here, you need to use the 4x4 table. So I hope this is clear. All right. In the final, I will not give you a very complicated situation. So in the final exam, so we will assume like four genotypes are. So for each locus, let's see. Okay, so in the final, we're gonna assume. So I will give you a easy problem, a straightforward problem. So suppose this is the 4 possible genotypes from the F2 design, right? And as you can see, we have like 1, 2, 3, and 4 genotypes, so corresponding to this 4 row or 4 column, right? All right, but if you look very close, if you look at this 4 genotypes, you're gonna see like 2 of them are actually very similar to each other. Actually, the genotype of these two genotypes are identical, just because like a different allele from different parents, right? So, so in practice, usually these two cannot be distinguishable. But in final exam, so I will give you an easy situation. So suppose we can successfully distinguish these two genotypes. So that will make your computation a little bit easier. So this is the plan. Okay. So for example, this is the case. So suppose we can easily distinguish the genotype number 2 and number 3 from each locus. So then what is the probability? So I will give you some question like this. So what is the probability that you're going to see a progeny carrying this genotype? So that's very easy, right? So this is how we do this. It's very clear because there's no confusion. So from the locus A from 1 to locus B, genotype 2. So this is the well-defined value here. And from B to C, genotype 2 to the 3. So that's very well-defined, the value. But in final exam, I'm gonna, so this is the simple algebra calculation. I will ask you to write some code, R code, to do this using the matrix notation. Yeah, you just follow. So don't worry, you just follow the example I gave you. You can try this. So once, if you have any problem or question to complete this calculation, we can discuss how to do this next time. Just give you some practice here. Right. Okay, so this is more real but complicated situation, right? In practice, usually, like if you have a genotype like this for the locus B or C, so there are two possible possibilities, right? Because either you got the B allele from mother, the B1 allele and the B2 allele from father, or the other way. So there are two possible ways to get this genotype and this genotype at these two loci. So we need to consider this. So in the computation, this is how we do this. So we have to consider all possible, all the probabilities, probability that can produce this genotype, right? The same here. So that's why we need to sum these numbers. But it's okay. So this is just for your just for your information. But we will not use this like complicated situation in the final exam. Okay. And so this slide shows how, so for this more complicated but a real situation, so how we use the matrix notation to help us to do the calculation. This is why we always use a matrix. Why? Because it's easy, straightforward. You don't have to do the summation. So in matrix, if you just specify, for example, for the locus A, if the genotype is the first, genotype equals to 1, that's very definitively defined, right? You just put a 1 here, so no doubt. There's only one possible way to generate the genotype of 1 at this locus, if this is a F2 design. However, if genotypes for this locus takes like A1, so this is 1, right? Sorry. So this is 1, but for 2 and 3, the genotype is something like this: A1, A2, or A2, A1, right? So if we cannot distinguish these two, then this will bring some like uncertainty, right? That's why to denote this kind of genotype here, so we put one here and one here to represent, okay, this genotype could come from this possibility or this possibility. All right. So this is what we need to do. So using the matrix, this is the only thing we need to consider. Once you well define this matrix, design matrix, genotype design matrix, then it's easy. You always use this formula to do the calculation. If you put 2, 1 here, the matrix calculation will automatically sum these two probabilities together. So you don't have to do this to do this manually, right? So the matrix can help you to do this. So it's very convenient. So that's why in coding we prefer using the matrix notation. All right. So for the fourth genotype, which is A2A2, it's also very clear. So this is well defined. We just put 1 here to represent this genotype. Is that clear? Any questions? Okay, good. All right. So four-way. So four-way design is a special, a generalized. Excuse me. Four-way design is actually a generalized format for F2 design. So F2 design is like the two F1 parents are of the same genotype, right? That's F2. But in the four-way, as you can see here, so we start from 4 totally different parents. They have like 4 different alleles, pure line at each locus. And if we cross the first 2 parents to get the F1, the first F1, the genotype is like this. And the same for this F1 parents, right? If we cross the parent number 3 and number 4, and at this locus we have 4 different alleles. Suppose we can completely we are completely able to distinguish these 4 alleles. This is not a big deal, right? Right now we can do the sequencing. If like these 4 alleles represent 4 different like numbers of the repeats, then it's easy for us to distinguish them, right? So yeah, that's the marker. All right. Now, if we cross this 2 F1 parents, and we're gonna get the progeny like this. So actually, this 4-way design is a very, it's a straightforward way. It's an easy way because we can easily distinguish these 4 different genotypes from the progeny, right? Can you see that? Yeah, it's very clear. All right. So if you compare the F2 with the 4-way, yeah, that's the difference because 4 different genotypes are totally distinguishable. Which means like if you use the same strategy to calculate the joint probability for multi-loci in a 4-way design, this will be a relatively easier job for you. So for example, this is the 4-way, and yeah, actually I can in the final I can give you a 4-way design and ask you to calculate the probability of this genotype. So for the first loci, it's genotype number 3, the second locus 1, and the third locus 4. So it's easy. You just use the matrix and to get the answer. So that's very straightforward. Okay. All right, let's look at some like even more complicated situations. So yeah, this is something that you in the future, yeah, if you're dealing with like genomic analysis, so you're gonna see something like this, incomplete genotype information. So when you do the coding, our coding to analyze your data. So sometimes like for some loci, the information is not that complete. So for example, if for this design, you got the two parents like this, so you have 3 alleles. So the first parent is a heterozygous A1, A2, and the other one is the homozygous A3, A3. If you cross these two, you're gonna get the genotypes, 4 possible genotypes like this, right? But the first two look identical, and the second two look identical. So in this case, you cannot distinguish between the first two and the second two genotypes, right? So we knew how to do this in the matrix, so we don't worry about this. So if you do the simple algebra, so probably you have to be very careful to follow the logic to in order to avoid any mistakes. But in the matrix notation, it's easy. So for this situation, you just, because you cannot distinguish the first one and the second one, you just put 1 and 1 here. So you're going to add up these two possible probabilities in your calculation, right? The same thing for the second and for the other genotype. So because for the other genotype, you cannot distinguish between this, the fourth and the fifth, the third and the fourth genotypes. Sorry. So you just put 1 here and 1 here to represent this genotype, which can come from this two possible way. Any questions? So this is how this. So I hope, yeah, this slide shows how beautiful the matrix notation will be. So it's so convenient for you to use matrix in your coding and computation. It's very easy. So and sometimes like it can avoid a lot of like mistakes, errors when you do the simple algebra. All right, so this is an example, right? Okay, so suppose this is more this is kind of like more real situation. So for example, even for a F2 design or a 4-way design, so you're gonna have some situation like this. So for the first locus A, see, you have like 3 alleles, right? And if you cross these 2 parents, you got this 2 genotypes, right? So which means like you cannot distinguish these 2, and you cannot distinguish these 2, right? This 3 and 4. So that's for the locus A. But for locus B, you may have totally different situation. So look at here. So you have like this and this for these 2 parents. And then, so for B, you're going to get this genotype, and this genotype. All right. 3, right? You cannot distinguish these 2. But for C, so we have some other situations. So if you cross these parents for locus C, you're going to get this genotype, and this genotype, and this genotype. So you cannot distinguish between them and them, right? But if I ask you to calculate the probability of this genotype in the progeny, all right, so you need to consider each loci separately, right? So this one is like this too, right? So because for this genotype, there are 2 possible ways, 3 and 4. So that's why we put like this. But for the B locus, that's very easy. There's only 1 possible way to get this genotype for this locus. So B is well defined, right? B equals to 1. Is that clear? Yeah. And for C, so if we want to calculate the probability of this genotype for locus C, so there are 2 possible ways to do this, right? That's why we put like 1 and 3 here. Is that clear? This is how we handle the more real situation. And to define this genotype, so this is the probability. This is the one we want to calculate the probability, right? For this genotype, we're going to put 1 here and 1 here to represent this, because these two genotypes cannot be distinguished from each other, right? For this genotype, it's easy. We just put 1 here at B locus. Is that clear? For this genotype C1, so there are 2 possibilities. That's why we put 1 here and 1 here. Yeah, don't worry. Yeah, this will not be on your final exam, but I hope like you can understand this, and in the future, when you want to use this strategy to do some computation for your real data, so this is the way how we handle this. All right, hopefully by doing some practice, you get familiar with the matrix notation computation, and then in the future, maybe you can apply some of this strategy in your own research project.
Dr. Jia, I have a question.
Sure.
For C equals 1, 3, how did you create the matrix? Because I'm curious about how you created the matrix given the 3 position.
You're talking about this one, right?
Yes.
Okay, so this is the matrix. Okay, so for example, so this is the genotype of the progeny we're interested in, right? And for the C locus, it takes the genotype like this. All right. Okay, so when we go back to the parents, the two parents have the genotype like this, right? So if you cross this genotype with this genotype, these are the possible outcomes from this cross, right? And yes. Okay, let's see. So which one from these 4 possible outcomes will produce the genotype like this? So this is the possible one. This is the possible one. Not this one and not this one, right? So, and we already knew, so we label this one as 1, 2, 3, and 4. So the 1 and the 3 will be the one that could generate the genotype like this. So that's why when we use this matrix DC to represent the genotype of this, we put 1 at the 1 locus here and 1 here to represent the 3rd one.
I see. I guess my question is, how do you decide the order of the genotypes? C1, 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 C2, C1, 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 C1.
Okay, so this is like arbitrary. It's up to you. But once you fix the order of this, you have to apply the same order for all the loci A, B, and C. So, for example, okay, so if you think this is from let's say, so let me, that's a good question. Yes, very good. So we label this allele as 1 and this allele as 2 from the first parents, right? This allele using 3 and 4. So, okay, now if you want, so the 1 can be matched with 3, right? So if you choose this order, and the 1 can also be matched with 4, right? These are the 2 possible outcomes, right? The 2 can also come together with 3. Do you agree? And the 2, this one.
Yes.
Let me use another notation. So 1, 2, 3, 4. We keep using this. Let's say this is or I use let me use this. Yeah. Yeah, you got my point. I
see what you mean. Yeah.
That's 1 and 2. That's the allele, okay? 3 and 4, okay? So the 1 allele, so think about the cross. So during the meiosis, so the first parent can produce 1 and 2 allele, right? And this 1 and 2 allele can come together with the 3 allele from the other parents, right? Or the 1 can come together with the 4 with the other parents, right? This is the same for the allele 2 from the first parent. Oh, sorry, this is 3. My apology. So the number 2 can also come together with, think about this is a zygote, right?
Mhm.
Okay. And this is the zygote. The number 2 will come together with the number 4. Okay, so this is arbitrary order. You can choose like the other way, but once you fix this order, you just follow this for all the loci A, B, and C.
So you just have to pick one and be consistent throughout your equations.
That's correct. So,
Okay.
so once you determine this order, so you know how to put this ones in this matrix, right? Yeah. So this is how we do this. Yes. Very good question. Thank you for asking this. Yeah.
Thank you, Dr. Chia.
Yeah, sure. Yeah, this is important. If you if you are not consistent with these orders, it will be messed up. Yeah, everything will be messed up. Thank you. Yeah. Okay. See, so once you use this matrix notation, you simply use the same the matrix calculation, and this will give you identical results, but in a much easier way, right? So I hope like you can appreciate the beauty of using matrix notations in your coding. So it's very easy to handle. Yeah. Okay. So okay, so actually the backcross or the F2 are a special case for the four-way design, right? Because they all follow this kind of like the layout. And in the backcross, it's easy because we cross this one as this one. Still, if you label this as 1 allele, 2 allele, 3 allele, and 4 allele, you're going to end up with this 4 possible combination, right? Because these two are completely like identical. So that's why we can easily combine this to use a 2x2 transition table. I hope this is clear for you. Yeah. So backcross or the F2 are actually the special cases for the four-way design. Right. So this is another way. So it's so usually like this is a more sophisticated way to do this, but I don't recommend this because this is not easy to handle in your code. But just for your information, so for the F2 design, because in usually like 1, 2, 3, 4, we have 4 genotypes, but usually the genotype number 4 and the number 3 they cannot be distinguished from each other. So then we sometimes we can simply combine these two together, right? So that means like in the transition matrix, instead of using 4x4, you can do the 3x3. The same, right? If you combine these two. But the problem is like, so this 3x3 matrix is no longer a symmetric matrix because of the, so if you look at here and here, they're not identical, right? Yeah, this is the only problem. So some people like using this, but I don't recommend this. So I think maybe the classical 4x4 is more it's more easy for us to control the errors or mistakes. So this is just for your information. And and so if you choose to use this way, so your design matrix to represent the genotypes for each locus will be a little bit different, right? So instead of using the 4x4, now the 3x3, and you have 3 genotypes. So you put 1 here to represent the first one here to represent the 2 in the middle, right? And the last one to represent the fourth one. Yeah, something like this. All right. So this is in old time, like, so if we do not have like very so in old time when we did not have the powerful sequencing or genotyping strategy, so researchers sometimes use the phenotype to infer the genotype. If there's like the dominance or recessive relationship between two alleles, for example, during the F2. So if this is F2 design, we have this 4 genotypes, right? But if like the first allele is dominant to the second one, if we cannot if we could not use the genotyping strategy, if we can just use the phenotype to infer the genotype, then these 3 will look identical, right? Yeah, so that's why you put 3 ones here, right? Because you don't know which one is which. So just like this, or the other way. So you put like one here. Is that clear? So this is the same way that we handle the missing value or uncertainty if we do not have the powerful genotyping sequencing method to distinguish the genotypes among these 4. So if totally missing, then we put what? We put 1 everywhere. So yeah, this is for the totally missing data. It's easy to handle in the matrix notation. Yeah, so this is why, yeah. So when doing the coding, so when we are coding, so we always recommend using the matrix notation. It's more easy to handle. Yeah. All right. All right. So now, once we know how to do this, so this is another important thing that we can do in your future project. Even we have a very advanced, powerful sequencing, genotyping technology. When you hand some sample to some like a private company, so they're going to do this sequencing or genotyping service for you. But when the data come back, so usually you're going to see for majority of your data, yeah, they probably can guarantee like very high quality genotyping results. But for some loci, so it's very likely you still get some missing data. So for example, yeah. So for example, in this chromosome, so you are very interested in the genotyping information at this locus, but unfortunately, the data is missing. However, you still get a very high quality genomic data for the 2 loci around this missing loci. Then what we can do is like we can use what we have learned, the multi-loci analysis, the strategy to calculate the possible genotype for this missing locus based on the 2 flanking markers. Does that make sense? So this is what we can do. So we also call this like the missing data imputation. So if you want to do the genotype imputation, so this is the strategy you can use. The rationale behind this is like, because those 3 loci are tightly linked, so they are somehow in the LD, right? The linkage, this liquid. So I always have problem to pronounce that. So LD, the linkage, this equilibrium. Yeah, okay. Which means they are tightly linked with each other. So if this is the case, the 3 loci actually will co-segregate during the meiosis, right? So they always like being inherited together through the meiosis. All right. Now, if they are tightly linked, if we knew the genotype information for these 2 flanking loci, then we can use the Bayesian method or the way we just learned, the multi-loci analysis, to infer the possible genotypes for this missing locus. Okay, so this is how we do this. So suppose we want to calculate the probability of a specific genotype at this locus, given the genotype data for these two flanking loci, two flanking markers. So this is how we define, right? We have learned this conditional probability. So this probability is actually equal to this. The joint probability of these three given divided by the probability of these two observed flanking markers. All right. So then how do we calculate this two? So this joint probability, so based on the Bayesian theorems, right? We can rewrite this probability in this way. And so this and this way, the Markov chain like this. So this step from here to here, that's the Markov chain we have learned, right? Excuse me. And once we have this, so how do we calculate the probability of the joint probability of these two observed flanking loci? So the joint probability for A and C actually equals to the integral of this probability by the missing loci, right? So and so if you have taken the statistical class, so usually this Bayesian theorem will be described, will be taught in your class. So this is how we calculate the joint probability of A and C from the joint probability of A, B, and C, right? Once we have this and this, we just follow this, right? So we can easily calculate the conditional probability of a specific genotype at this missing locus using this, right? This is this, and this is this. So this is the numerator, and this is the denominator. Okay. Okay. Right. So this is just an example. So I don't think I will put any questions like this on the final exam. So don't worry about too much about this. But I hope you understand this, and in the future, when you deal with some missing data in your own project, so you probably can think about, oh yeah, we have learned this in Dr. Jia's class. So maybe we can go back and find out what is going on there, and we can. So maybe you can start coding something like this to help you to infer the genotypes of some like missing loci. All right. And so this is an example. So I don't think I have time to go through this example. So I'm gonna leave this up to you. So after class, you just read through this example and see how we use this multi-loci analysis strategy to help infer the genotypes of any missing data here. So, and this is a generalized situation. So because when you get the sequence data back from the company, so it's very likely that you're gonna miss more than one the data for more than one locus, right? So how do you infer those missing data? A lot of markers, and using the observed data from the rest of the markers. So this is the extension of the 3 loci analysis method. All right, and this is only for your information. Okay, any questions before we move to the next chapter? All right, very good. So let me stop share this one, and we're gonna continue talking about chapter 5. Okay. So in this chapter, we're going to learn some very basic concepts of quantitative genetics. Because quantitative genetics, we usually study a population, right? And so since we are focusing on genetics, so we are interested in genes frequency, and so in this class we only talk about the simple situation, the diploid genome. So for each genotype, there are like 2 copies, right? And it could be like the homozygous, the same allele, or different alleles. And we also want to study the allele frequency. Other than the gene frequency, we also want to study the allele frequency in a population. So this is this chapter we're going to learn some like very basic concepts or strategy to describe either the gene frequency or the allele frequency for a interested population. Okay. The first concept I'm going to introduce to you is the Hardy-Weinberg equilibrium. Okay. Right. So this is the concept here. So usually the Hardy-Weinberg is describing a ideal situation. The ideal situation means like, so in a population, and this population can generate the first, second, and so on the generations by itself, right? And so in a ideal condition, the allele and the genotype frequencies in this population will remain constant from generation to generation if there's no other evolutionary influences. So what are those like other evolutionary influence? So those are the terms. So probably you are familiar with this, and so if some of the terms are not very familiar with you, you are not very familiar with them. So after class, you can search them using the Google to make sure you understand the concept of those. So those are some like factors or the causes that can influence the evolutionary. So if some of these forces or factors exist, it will change this ideal condition, which means like if there's some, for example, if there's like selection forces, so the alleles or the genotype frequency will no longer follow this Hardy-Weinberg equilibrium. So let's see how this works. All right. Another thing is like, so of course, in under this ideal condition, the allele genotype frequency will follow this Hardy-Weinberg, right? So we usually treat this as a non-hypothesis ideal situation. However, if there's some like other forces, evolutionary forces, for example, if there's a selection, and if the selection worked on this population, and you're gonna see some deviation from the Hardy-Weinberg, right? And that will be our alternative hypothesis. So which means like you can use this ideal situation to test whether this population is subject to some like external selection force. Does that make sense? Yeah. So the non-hypothesis means like if there's no other forces, this will allele and the genotype frequency will follow this Hardy-Weinberg. However, if there exists some like other forces, selection forces, for example, you're going to see some deviation from this Hardy-Weinberg equilibrium, and we can use this to construct a hypothesis testing, right? So we have 2 competing hypotheses here, and we can use this to test the existence of any like selection forces. Any questions here? Okay. All right, now let's see how this works. Okay, Heidi Weinberg. Suppose this is the population and the first generation, this is the first generation. Suppose in this first generation, the allele frequency, the frequency of the alleles, we are talking about two alleles. So in this case, at this locus, we have like big A and a small a. And in this first generation of the population, suppose the big A allele frequency equals to P, and the little a is Q, and the P plus Q must be equal to 1, right? All right. Okay, now suppose this is the pool of these two alleles, and if we so we can easily calculate the gene frequency in this first generation, right? Because this for the big A, the probability, allele probability equals to 0.3 and little a is 0.7. So what's the chance to have the individual of genotype like this? So it's easy, right? So we just use this to calculate gene frequency. Any questions here? The same for this one, right? The genotype for this individuals in this population will be Q squared. And for the heterozygous, there are two ways, right? Either you got a big A from mother and a small a from father, or the other way. So you must multiply this probabilities by 2, right? And this is how we calculate the gene frequency in the first generation. Any questions here? Okay, so this is the gene frequency in the first generation. Okay. Now, if we, this is the gene frequency. Any questions here? Yeah, so sorry, I made a mistake. So this is the first generation, and this is the allele, the pool of the alleles from the first generation. If we do the random mating, this will be the second generation. The gene frequency in the second generation. And okay, now once we got the gene frequency for the second generation, we can easily calculate the allele frequency for each of these two alleles in the second generation, right? So this, since we have 9% of the genotype of big A, and we have 42% of the genotype of the heterozygous like this, and this is the homozygous little a. And if we want to calculate the allele frequency for the second generation, so this will contribute 2, right? This will contribute half. So this is how we calculate this. And when you calculate the allele frequency for the big A in the second generation, it is the same with the first generation. The same thing here, right? If we want to calculate the allele frequency for the little a in the second generation, you can see it remains the same with the allele frequency in the first generation. Is that clear? And in the final exam, probably I can ask you to prove. So if for example this gene, we have like 2 alleles in the population, and how do you prove this allele frequency will remain the same if there's no other evolutionary forces to influence this population? So you just show me. So in the first generation, this is the allele frequency, and during the random mating, you're going to generate the second generation, right? This is the second generation. And for the second generation, you're going to calculate the gene frequency first. And based on this gene frequency, you can calculate the allele frequency for this second generation. And once you got this, you can show me, okay, in the second generation, the allele frequency for big A and the small a remain the same with the first generation here. Does that make sense? Good. All right. And this chapter actually some concepts, if you have already preview some of the slides, you're going to see some concepts are kind of like very complicated. So so that's why. So today and on Thursday of this week, so we're gonna move slowly to make sure you are comfortable with all the concepts introduced here. So this is very important. Okay. So here we use some like statistical notations to help us to describe this gene or allele frequencies for a population. So for example, if we want to calculate the gene frequency for this genotype A1, we use the P11 here, then it's easy for us to understand. So we use this P12 and P22 to represent the gene frequency for these three genotypes in the population, right? And we use the little p1 to represent the allele frequency. So the allele frequency means like in this population, what is the fraction of the allele of this type? So since the A1 will came from, the allele A1 will come from two sources, right? I hope it's clear. So the A1 can come from this genotype and half of this genotype. So that's why when we calculate the allele frequency for A1, we're going to use the probability of this genotype and half of the probability of this genotype. Does that make sense? The same thing for the second allele frequency, the same thing here. This is important because we're going to use this to do the expectation calculation in the following slides. All right. And based on the Hardy-Weinberg equilibrium, so you're going to see the relationship between this, right? So this is actually very similar to the presentation by the binomial expansion. So this is how we do the binomial expansion, right? If we do the A1, A2 square, and if we can expand this, this will give us like this. The same thing for calculating the allele frequencies for this population. Any questions here? Okay. All right, now, yeah, I believe this is the most confusing part. So please pay attention. Yeah, and there's some like terms for us try to link the statistic terms to the genetics terms. Okay, so when you study a population, for each individual, we're going to use the Y11 to represent the phenotypic value you observed for the individual 11, the individual with the genotype of A1. Any questions here? We use the Y11 to represent the phenotypic value for this genotype A1 and A1, say from the backcross design. Think about like some phenotypes, for example, the yield. So if you are doing a backcross design using a rice population, a rice, and this Y11 may represent the yield for this genotype, and during the backcross design or F2 design, you may have many replicates progeny having the same genotype, right? So which means like you can observe a lot of values, phenotypic values for the genotype of this type. And if you plot the data of this genotype, you're gonna see some normal distribution like this. Does that make sense? Any questions here? Okay. All right. So for a specific individual of this, so we can use this to represent the observed phenotypic value. So this observed phenotypic value actually consists of two parts. The first part is the real the first part is the expected phenotypic value. We use G11 here, plus some random error term. And the reason why, when you plot a lot of like these phenotypic values, you're going to see they're not identical. They follow a normal distribution because of this error term. Does that make sense? Okay. Now, if you average your observed phenotypic value, this is the average. You see the little bar here, right? And this will be equal to the expected phenotypic value of this genotype plus the average of the random errors. And in statistics, we usually assume this average of the random error equals to 0, right? So if this is the case, so this equation holds, right? Which means like when you have multiple observations for this genotype, if you average this replicate or the multiple values, observed value for this genotype, this will give you the expected phenotypic value. Does that make sense? So that's why we always like calculate the sample mean, and the sample mean will give us the best estimation of the population mean. All right. Okay, now in the F2 design, we have 3 genotypes, right? We have A1, A1, A2, A2, and A1, A2. And we use the G11 to represent, this is 1, to represent the expected phenotypic value for this genotype, and the G12 to represent the expected phenotypic value for this genotype, and A22 is the so the G22 is the expected phenotypic value for this A2 genotype. All right. Now this is something new to us. So we're going to define the first one. Mu is the midpoint value in this F2 design, and we use the little a to represent the additive effects. I hope you have heard of this kind of like terms, additive effects and the dominant effects. So we use this 3, and this is how we define these 3 terms. The midpoint is easy, so we just look at the 2 extreme phenotypes here. So this is the phenotype, expected phenotype for the first genotype, right? The third genotype, this is the expected phenotypic value for the third genotype. We want to see the midpoint of these 2 extreme values. Yeah, this is the midpoint. So in this diagram, you're going to see this is the midpoint between this one and this one. Okay, now what is the additive effect? So this is totally the genetic terms. So when we talk about a single locus, if this locus has some influence on a trait of interest, then we can use the 3 terms to define the different genetic effects. The additive effects means like, if you look at the first extreme phenotype here, what is the difference between this one with the midpoint, right? That's the additive effect, the same here. So if you look at the difference between the second extreme phenotype with the midpoint, that's the additive effects. There are 2 additive effects here. So this is how we define this. So this is equivalent to the midpoint, G1, 1 plus G22, minus G22. Does that make sense? So that's the additive effect, right? And the dominant effect is defined in this way. Dominant effect is defined as the difference between the phenotypic value of this heterozygous genotype with the midpoint. So you're going to see the difference here is defined as the dominant effect. Is that clear? Dominance effect. The difference.
I may have missed. Why are we taking these values to begin with?
Oh, okay. You mean this values here and here?
Yeah, no, I guess like I'm kind of confused as to why we're considering mu, A, and D.
Oh, why we consider this? So yeah, because okay. The reason why we consider this because this will help us to do the following. I'm going to show you later. Yeah, the reason why we want to use this, right? Because so later on we're gonna use these terms here to calculate the genotypic value and the breeding value. See, this is for our own convenience. Once we can well define this additive effects or the dominance effect, we can use these values to help us to define the genotypic values for each genotypes for the whole population. And then we can easily calculate the expected genotypic value for the whole population and the variance. Because in genetics, sometimes probably you have heard the heritability, right? The heritability actually is defined as the proportion of the variability, something like this, that can be explained by the genotype variability. So to define all these values will help us with the calculation in the following part. Did I answer your question?
Yeah, that makes more sense for the context. Thank you.
Oh, sure. Yeah, so that's why this is very important for us to understand those concepts for now. All right. All right. So let me ask you a question. So you all took genetic class and when you were in the college. So in your genetic class, did the professor mention the additive and the dominance effect in your population? Yeah. Okay, cool. That's very good. So this is exactly the identical things we're talking about. So that's the additive and the dominance effect. So this is here we just try to define this genetic effects using a statistical way, because we try to use statistical method to help us to dissect the population, right? All right, so this is how we define this, the midpoint, the additive effect, and the dominance effect, okay. Okay, so now expectation. So I hope I can give you some like very brief review about some important concepts in statistics. The expected value. The expected value, if we want to calculate the expected value for a random variable, so this is how we calculate this. So suppose we're tossing we are rolling a dice, and this die can give us like 6 possible outcomes, right? Either 1, 2, 3, 4, and 6, and 5, and 6. And suppose this is a failed die, and which means for each of these 6 outcomes, they have equal chance to show up, right? That's why for each one, you're going to see the 1/6. That's the probability associated with each outcome, all right? And with this information, how do we calculate the expected value for this random variable? So this is the formula. We are going to sum this together, and each term represents the product of this outcome value with its associated probability. Does that make sense? So if you do this calculation, if you roll this dice many, many times, like 100, 200, and so on, 1,000, you're going to see like eventually it will be very close to the expected value, which is 3.5. So this is how we calculate the expected value or mean. Right. And the same thing like this. So if this is so how do you call this? Like if we play this this game, like there are like there are like 8 outcomes, 1 through 8, and each one has the same probability. So we can easily calculate the expected value of X, right? And so we sum up all possible outcomes and divide it by the number of the total number of outcomes. Since they are equal, so the probability for each one outcome will be 1/n. So this is how we calculate the expected value. This is another example, but this one, the 2 possible outcomes with different probability. So when you go to Las Vegas, if you are interested in playing this game, like the roulette game, and this is how the game works. So there are like a total of like 38 numbers. If you bet the right number, each time you just put $1 on the bet. If you bet the right one, so you're gonna get $35 back. So you're going to win this. However, if you didn't bet the right number, you're going to lose this $1. So for a long run, what is the average expected gain from this game? So this is a classical example that we can use to show the calculation of the expected value. So this is the expected gain for a long run. So each time if you lose, you lose $1 with the probability like this. This is the probability associated with this outcome, right? The lose. If you win, so you're gonna get this many. Oh, this is a significant number. However, the chance is associated with this outcome is like this. So if you do the sum of this to calculate the expected value, which is negative like this, which means like in the long run you're gonna lose eventually. Hopefully, like you understand how we calculate the expected value. This is the formula. We just sum the product of each outcome with its associated probability. Any questions here? Right. And so I think I'm going to stop here. So today we introduced some like basic concepts for statistical genetics. So any questions so far for today's lecture? Right. Very good, thank you. So so for the rest of the time, so have you had chance to practice the practice assignment? No? Okay. Yes. So do you have any questions for me? So okay, very good. Yeah, I gave you a very simple example to show how you can use the 2x2 table, right? 2x2 transition matrix help you calculate the joint probability of 3 loci in the backcross design. So this is the basic situation. In the final exam, I expect each of you can expand that strategy to analyze a little bit more complicated situation. So in F2 design, so how you can construct the 4x4 transition matrix and write the code to do the calculation for a joint probability of any genotypes. Okay. All right, I'm gonna stop here today. So if you do not have any questions, you will be dismissed. For today. And so if you haven't practiced those assignments, please do so. And once you have any questions, please bring those questions back to me on Thursday. We can have like discussion part to solve your problem, and if you have any.
Thank you, Dr. Jia.
Thank you all. Okay, have a nice day. Bye. See you next time.